Okay, so in this lecture I want to a little bit talk about the reverting the idea of Fourier transform back into the original function. So we have this idea of Fourier series and inverse Fourier transform. And the basic idea here is this idea that how could you use the Fourier coefficients that we defined to get back into the original function? So there's this theorem, I think this is a theorem 4.6 in the notes, which says the following, that for any f from zp to c, any function, we have that f at the point t is given by a sum 1 over p in weight in front, t in zp, and we take the Fourier k actually here, k in zp, fk Fourier transform, and e to the power 2 pi I k t over k t over p. So recall that the Fourier transform of k was given by the sum of t in zp ft e to the power minus 2 pi I kt over p. So using these coefficients, you can actually write every function t in zp at this way. So no matter what function is. So here you don't have any issues with about how nice your function is. It doesn't matter what function you use. You can still always do this computation. And let's prove this now, which is quite a simple proof actually. In this is one of major big theorems in normal Fourier analysis on the real line. It's very difficult to prove something like this, especially of course, it doesn't even hold for all functions, but even for quite nice functions, it's quite difficult to prove this result. But it uses similar idea. In the end, it kind of reduces to the same kind of strategy that we are going to show you now. So if you want to prove this, let's just use the definition. So let's open up the this definition. So we take this sum here. So let's actually take this whole expression without the 1 over p, so that we have this expression, and let's start to open this up. So open the definition of Fourier transform. So this is k in zp, and then this is t in zp. Actually, let's use an s here because that's the other one, fs e to the power minus 2 pi I k s over p, and then that's the definition of the Fourier transform of k, and then you have e to the power 2 pi I k t over p. Okay, so that's the definition, and now we just basically swap the order of summations to make this work. So we swap the order over here, and we obtain s from zp and then k from zp, and then you still have the f of s, and then we have these coefficients minus 2 pi I ks over p e to the power 2 pi I kt over p. Okay, and now we can basically do the following, that we can also move this f as here. So we can open this up, so we can put this s in zp, we can put the f of s here, we can keep this summation k in zp here, and then we can put these things together. So we can actually open this up into minus 2 pi I, the k, that's also a common term, and then we just can put here s minus t over p in this way. And what's the purpose of this is that we see that this number here, we can write this as k in zp. We can write this as e to the power I theta k for theta, which is equal to minus 2 pi t minus s, I think, over p. When you put the minus, then you should get this quantity in the front. Oh, sorry, s minus t and s minus t. Yeah. So now we can use the exponential sum formula. So here, this k from zp of e to the power I theta k, this is actually k from 0 to p minus 1, then this is equal to, so first of all, let's assume that theta is, this t is not equal to s, which implies that theta is not equal to 0. Then in this situation, we know that this whole summation is equal to, by the exponential sum formula, 1 minus e to the power p theta I and 1 minus e to the power theta I. That's the exponential sum formula. And now if you open this up, you have this is e to the power I. If you multiply it by theta, you get minus 2 pi s minus t. And then here you get 1 minus e to the power minus 2 pi s over t divided by p. But as s minus t is an integer, this implies that 1 minus e to the power minus 2 pi s minus t, this is equal to 0. So thus this whole thing is equal to 0 at this situation. And so this is in the case when t is equal to 0, and if this is equal to, if t is equal to s, then this is just equal to a summation of k from 0 p minus 1, and this is actually then summation of ones. That's the only thing that you get in the other situation. And and that's equal to a p. So basically we have two situations. We either have that it's equal to 0 or it's equal to p, depending on when t is equal to s and when t is not equal to s. So that's the two situations that you see here. So that means that the whole summation with sum from k from 0 to p minus 1 of e to the power I theta k, then this is equal to just equal to p and 0 and p, and t is equal to s. T is not equal to s and t is equal to s. So that's why in this summation that we have here, if you remember that we are summing over these massive numbers, so we know now that this expression that we have computed here is just equal to p when t is equal to s, and it's just equal to 0 for any other possible choices. So that's why we can take this expression here. Let's take this whole thing, paste it in here. We see that this is equal to summation s equals zp, and now we know that this expression here is equal to p and 0, t is equal to s, t is not equal to s. So we just get that this is equal to p when it's equal to s. So when the t is, the only possible choice that you have here is this possible choice that this is equal to s, and then this at that point this is equal to 0. So the only thing that remains here is f equals t. So that's the only possibility that remains. And now what we have now proven is that this whole expression that we have above here, so this one where we started from, let's copy this down here. We have just proven that this expression is equal to ft p. So this implies that f of t is equal to, as we claim, 1 over p k from zp f Fourier transform k e to the power 2 pi I k t over p, as we claim. So that's the proof, and using this expression we can then immediately define the notion of inverse Fourier transform. So that's the only thing I wanted to say about the inverse Fourier transform is then using that Fourier sum formula we just have above here. So Fourier transform is just defined to be that, let's call it, if g is a function from zp to c, then we define the inverse Fourier transform at the point, let's say t, to be this 1 over p k in zp, g of k, and then e to the power 2 pi I kt over p. And this is defined for every t in zp. So thus we have the following, that if f is a function from zp to c, then Fourier transform of this f, well, actually, if you take the Fourier transform and take its inverse Fourier transform, then this is equal to f. So that's what the Fourier series was above here. Like if you look at this Fourier series expression up here, ft, this is just on the right hand side, is a Fourier series. So basically you just take the Fourier series of the inverse Fourier transform and then you get the same expression. Okay, so that's the kind of basics of Fourier analysis. So just the inverse Fourier transform, the Fourier series. And now in the final lecture of this week, I will talk about this notion of spectral gap, which is a notion that comes from the random walks, and then talk about how Fourier transform might help us to maybe study something about the spectral gap. So that's all. Thanks.